Hello everyone and welcome to a new discussion which basically it is a continuation of our earlier discussions on derivatives of DEMs, but those we kept focused mainly on slope and aspect, though they are also part of our terrain analysis, and but we put them in a common derivatives, very common derivatives or standard derivatives of digital elevation models. When you use the raster data set like a digital elevation model or a surface, you have to create slope and aspect as you have seen including in our demonstration. Whereas when you use a tin model, there you do not have to create separate slope and aspect maps. The slope and aspect maps are created simultaneously once tin is created. So, for terrain analysis definitely you need not only slope and aspect information or maps, but many other informations also. So, this discussion will go on about the derivatives of different derivatives of DM, and we have seen two major one, slope and aspect. Now, we will continue on this. So, as you know that this terrain analysis includes basically analysis and interpretation of topographic features. This here I would like to spend some time on interpretation, and why it is very much required, because earlier when we did not have much digital data and people used to have prints of, say for example, aerial photographs or satellite images or even a topographic maps. People used to study these things. That means people used to interpret these things. I remember that we were told to study the topo sheets. That means we are interpreting a topo sheets, looking the contours, looking the drainage pattern, and looking other features which were present on a topo sheet. Similarly, same with the satellite images. So, this analysis and interpretation, rather than focusing more on processing, because things were not in digital form. So, rather than focusing on processing, our focus was on interpretation and analysis. And so, definitely whatever the data you get, one should analyze things. Like when we were seeing the demonstration of slope and aspect, then the software may support various types of methods. So, which one is suitable for that particular data set which belongs to my area of interest, then I can try few methods, can create various products and then compare them, do the interpretation, analyze them whether things are in order or not. So, this is the analysis and especially the interpretation, and that focus should always be there, whatever the data, whether satellite data or digital image or your digital elevation models or even a topo sheets. And this lot of time should be spent on this, because processing can be done by a technician, but the interpretation or that is skill which you develop is unprecedented, which cannot be replaced by any machine. So, basically for terrain analysis what we do the analysis and interpretation of topographic features, and that means basically landforms, geomorphic landforms which are present on the land or the surface of the earth. And basically what we do in this GIS platform, that to do this kind of topographic features analysis and interpretation, we employ digital elevation models on a GIS platform. So, this is what is very simple words we can define what is basically terrain analysis is. And these features which topographic features which we are talking are, which includes the slope and aspect which we have already discussed. Also viewshed analysis again is very useful in many applications. Then elevation and differences and profiles and other things. Then contour lines, flow directions, of say water or some pollutants or other things, upslope flow lines and downslope flow lines, etc. All these, and there are various derivatives of digital elevation model. Most of those are part of terrain analysis, and in modern days we employ digital elevation model on a GIS platform and perform this terrain analysis. Earlier, when we didn't have these facilities, the terrain analysis was being performed either using aerial photographs or survey topo sheets. But now we are having advantage of having digital elevation models and GIS. Basically, the purpose of terrain analysis is to basically build mathematical abstraction of surface terrain in order to delineate or stratify landscapes. Whatever the landforms which are present, how they are there, can we represent them through mathematical functions and create an understanding of relationship between physical features and ecological processes. So, the two we can include under this terrain analysis. That means analyzing things related with the topographic surface in a comprehensive manner. So, not only you are doing a physical analysis or physical features are involved in your analysis, but ecological processes are also there. Now, as you know that areas of a sloping cell of a digital elevation model which has been subjected to create a slope map is not the same same size as one that lies flat. So, here what basic point is coming that when we go for this terrain analysis, the major thing is coming if an area is flat and say if I am having a digital elevation model of 30 meter by 30 meter, that means 30 meter spatial resolution. For flat area, it would be simply 900 square meter. Area would be 900 square meter. But if it is not flat and if it is inclined surface, then the area is going to be different than what is flat is, because this measurement which I am doing, or when we say spatial resolution, we are always talking in terms of horizontal plane. But when things are slope or landforms are having slopes or facets are having slope or inclinations, then the area may change because length will also change. So, this thing is important here, that the area of a sloping cell is not same size as one that lies flat. So, the flat one will always have less area, the length will also be less as compared to an inclined one. Now, the sloped cell occupies more area than a flat one. So, we can give a new term, or that when we say flat, it means we are talking to planimetric surface, and planimetric surface means we are talking about a flat surface in a horizontal plane, and whereas when we say surface, we are talking about inclined surface. So, the planimetric to surface area ratio is an index of topographic roughness, and this topographic roughness can become very useful input for various kind of analysis, like for example in erosional studies, in landslide studies, or in many ecological assessments also. So, planimetric to surface area ratio is an index of topographic roughness with has a wide range of uses. I have just narrated few, including habitat assessment to land use planning to geomorphology. In recent years, the maximum beneficiary of digital elevation models and GIS platform is geomorphology, and a new branch of geomorphology has emerged which is called quantitative geomorphology, and this is playing very important role. Quantitative geomorphology not only interesting and part of field of earth sciences and or geography, but it is also very important in civil engineering, especially related with hydraulics and other engineering. So, geomorphology, quantitative geomorphology is very, very important for many things, including your flood analysis and all. So, whatever related with water and engineering, their geomorphology can play very important role. And obviously, quantitative geomorphology can provide a direct inputs to various models which are used for estimation of flood inundated areas or snow melt runoff or many other things. Now, this index or this topographic planimetric to surface ratio, which we can also call as index, is largely independent of scale. So, whether you are using a 30-meter spatial resolution data or a 90-meter spatial resolution digital elevation model, still this ratio would be there. That means there will be a difference between planimetric surface, planimetric area and surface area. As we know that this is in our day-to-day life, that if we walk up and down in a steep terrain, we will walk far more than the planimetric length of your path. So, in flat or in planimetric length is always less than what you get a surface length in a hilly terrain. While we have known this fact for thousands of years, the surface area and the length calculations were particularly impossible to apply to paper maps such as topographic maps. So, using topographic maps, it was not possible to find out what is surface area or what is planimetric area or surface length or planimetric length. But with employing digital elevation model on a GIS platform, it has become definitely possible. GIS allows us to handle a digital elevation model and also allows us to perform such calculations. In a vector based GIS, area calculations are plane geometry equations, whereas in raster or in a grid based system, planimetric area is calculated by multiplying the number of cells defining a map feature times the area of individual cell. So, planimetry area calculation is very simple because we know the area of one cell and that ground area which is representing say 30 meter by 30 meter, that means 900 square meter, and if we are having 10,000 such cells in our data, and we will multiply by 10,000 to get the correct. For example, here if a forest cover types occupies 500 cell with a spatial resolution of 1 hectare each, then the total planimetric area for cover type is 500 multiplied by 1 hectare per cell equal to 500 hectare. Simple calculations. But when we go for surface area calculations or surface length calculation, then things will be different. Here both examples are given. This is horizontal plane or planimetric surface, and this is the tilted or inclined surface. As you can see here, of course, for our understanding, this has been exaggerated in this schematic. So, what this is going to be the minimal surface area if it is flat or when it is measured on a horizontal plane, whereas this tilted one or where the sloping surfaces are there, this will be increased surface area as compared to your planimetric area, which is depicted here that the cell though in our raster format or in a digital elevation model, this will be representing a square area, but that square area is not truly on the ground as a square, but it is a surface area. So, in sloping conditions, the area is going to be more. But if by mistake somebody does the calculation only using horizontal plane, then basically he is underestimating. And I tell you, I know various projects which have failed because people have underestimated the earthwork, for example. Using just planimetric concept and assuming everything is flat, like implying survey toposits, calculated the length, area and grossly underestimated the work. and later on such projects goes in real trouble. So nowadays it should not be done in that way. We should, if it is inclined area or slopy land, then the surface area should be calculated rather than planimetric area. So surface area increases with the increase in inclination. So in a highly rugged terrain, this situation will increase. That means the surface area will increase much more than in a flat part. It's like slicing a stick of water at increased angles of noting that changes in the surface area of our sliced or patties. So this is how, that is why it is very, very important to understand and this difference, that planimetry area or planimetry length will always be less compared to your surface area or inclined area. So this actual surface area of each grid cell is dependent on its inclination. So it's basically inclination dependent, and surface area, this we have already discussed, increases as a grid cell is tilted from a horizontal reference plane, that is planimetric, to its three-dimensional position in a digital elevation surface like here, which is we have just discussed. Now in a more little more complication I would like to add here, that in planimetric area, here you just multiply length and width and you get the area. But if the surface area is orthogonal, that means you are having an inclined surface which is in orthogonal fashion, then again you can calculate this one with length and width, where the slope is 45 degree and azimuth, that means with reference to the north, is 180 degree. But if it is non-orthogonal, like in this scenario, the surface area will increase further, and here the slope though remain 45 degree as in the previous example in case of orthogonal. However, the azimuth has changed, and azimuth is 135 degree. Because in nature it is not necessary that all the time the surface area would be orthogonal. Generally these would be non-orthogonal, and there you would have a, so this is a parallelogram scenario. So in orthogonal surface area is calculated as length times width, whereas the width is adjusted by slope angle. The example is given here, that like in this one, the 100 meter multiplied by 100 meter cos 45 degree, you ultimately come to 1.1414 hectare. If I do it in a planimetric fashion using a topo sheet, that area is coming just 1 hectare. But if it is non-orthogonal, then it is coming 11.414 hectare. See the difference, huge difference in the surface area. Instead of 1 hectare, it is coming now 11 hectare. And that is why I said when discussing with previous slides, that if a lot of work is estimated based on just planimetric surface, assuming everything in 2D using survey topo sheets, you are going to grossly underestimate the work, and that will cause lot of problems. So non-orthogonal surface area forms a parallelogram and is calculated in the same manner as orthogonal surface area. So again here 45 degree, cos 45 degree, 100, and then you end up with 11.414 hectare. So here this is 10,000 square meter, 14,144 square meter, 14,144 square meter. So one has to take care about this. In this particular example, orthogonal and non-orthogonal are giving the same area, but in some other situations there might be some differences there. But planimetric and surface area is going to be the difference. So the plane area, that means we consider in 2D, is always less than when we considered in 3D. So, surface area can be calculated by dividing the planimetric area by cosine of the slope angle, and this a grid location of 20% slope as a surface area of this much hectares based on solving the following equations, which we have already seen. And so, the 10 slope angle 20%, because 20% is our slope, divided by 100, and we get the this ratio. So, slope angle is arc 10, and this is this much degree of 11.3099 degree, and surface area factor, then this is multiplied with cos degrees. So, it becomes 0.980, and ultimately then surface area equal to about 1 hectare, and so we get this kind of result. So, if we do the calculations for different angles, what happens? So, this is identification of surface area calculation for 1 hectare gridding resolution under several terrain slope conditions. So, when you are having slope say 20%, instead of degree here the example is in percent, and then the 10 is theta is here the angle is taken 0.20, slope angle is 11.399, and sloping factor surface factor is 0.98, and this surface area is about 1 hectare. If we go for say 100% slope, and then 145 degree, and then here 0.771, and here you are getting 1.41. So, as you can see here between these two, that there is a difference in the surface area. So, higher the angle, more the surface area is going to be. So, the surface area factor is independent of grading resolution, that is it is independent of a scale. Driving the surface area of a cell on a 5 hectare resolution map simply changes the last step of 20% above to 5 hectare, and you get the area. If I show the real examples, this is what on the left side which you are seeing a simple digital elevation model, and when we use as for calculations of surface area, this comes around and this much 8100 square meter. But when the same area is subjected to calculations through this surface area rather than planimetric area, then this is much higher as compared to that one. Because you know that the terrain is highly undulated and surface area is going to be much more. So, based on simple a digital elevation model which is in planimetric presentation, or a survey topo sheets, if I make estimations about sediment supply from a basin, or flow conditions, or erosion, or snow melt, then I am grossly underestimating these values. So, always it is necessary to take care if you are handling an area which you know that it is having undulation, it is rugged, it is hilly terrain, you must take care about this part. Otherwise, the purpose of GIS is not to introduce errors. The purpose of GIS is to bring new insight about the data which otherwise is impossible. And purpose of GIS is also to keep errors at the minimum. Even if there are inherent errors, keep them at the minimum, not to introduce new errors, because error propagates in GIS. So, if errors are not controlled in the beginning, then your results are going to be highly unreliable, and nobody would believe on solutions which are provided through GIS. GIS is a very powerful, very wonderful tool, but it should be handled with very much care, with full understanding about these intricacies. Now when we go for instead of a plane, whether it's inclined or surface, when we start looking at much smaller scale, larger scale means to a zoomed part or for a small area, then the surface curvature also plays a very important role. So, the surface curvature, let us define here, at a given point is the curvature of a line formed by the intersection of surface area with a plane and with a specific orientation passing through this point. We will see much more details about this and through our diagrams, figures also. So, the value of curvature is reciprocal of the radius of curve, the larger the radius. The smaller the curvature value is. A gentle curve has a small curvature and a tight curve always have a large curvature value, which the units here of curvature are in radians per linear unit and the unit of the spatial references of the raster. So, the here our units, if they are in our DD, then per linear units, that per linear DD. Now, curvatures can be of various types. So, first we will discuss the plane curvature, or when we consider curvature or a curved surface in a flat. Like here, the plane curvature is the curvature in a horizontal plane, like planimetric area. So, when we measure in a horizontal plane or we try to understand in a horizontal plane, then it becomes our plane curvature. So, it can also describe as the curvature of hypothetical contour line that passes through a specific cell. Like here shown various contour lines passing through various cells here. So, plane curvature is positive for cells with concave contours. Like here, the example here, the green one in this figure, they are all concave contours and we say positive or this contour when this is convex. And then and the plane curvature is positive for the cells with concave contours and negative for the cells with convex contours. The plane curvature can be used to differentiate between the ridges and valleys. Now, this plane curvature, also called plane curvature in some softwares or literature, is perpendicular to the direction of maximum slope. And this plane curvature is related to the convergence and divergence of flow across a slope. And convergence and divergence of flows, for example water, plays very important role in terms of erosion or in landsliding. So, here when we are having this values like here, positive values A, when you are having a convex surface, the arrows indicating that the movement is laterally convex at the cell, whereas in negative, that is like example B, which is concave, they are converging towards each other. And a value which is 0, that means the surface, though it is inclined but is flat, then you are having straight lines. So, these lines basically will decide whether they are convergence or divergence. Like here, example A is for convergence and example B for the divergence, and this is value 0. Now, there can be another curvature instead of plane curvature. Now, we talk about the profile curvature, and profile curvature is basically the curvature of the surface in the direction of steepest slope in the vertical plane of flow lines. So, as you can see here that this blue line and these others, they are creating a vertical plane which is going through this hillock, which is having 3 peaks. So, this entire part, if I color it, this is the vertical plane in which we are having this kind of plan profile curvature. So, profile curvature is the curvature of the steepest surface in the direction of steepest slope in the vertical plane of flow line. So, here now we will consider these slopes which will decide our profile curvature. So, when these are convex, we call as negative, because erosion will occur more on these convex profile curvature compared to the concave, which are shown here in the green color, are where the deposition might take place or less erosion will take place. So, profile curvature affects the flow velocity of water, draining the surface and influences erosion and deposition. So, negative or convex profile curvature will have more erosion, say E plus, and this will have simple E or may not be E at all. So, it influences the erosion and deposition processes. In locations with convex, that is a negative profile curvature, the erosion will prevail, and in locations with concave position curvature, the deposition might be there. Now, we continue with this discussion on profile curvature, that a profile curvature is parallel to the slope and indicates the direction of maximum slope, and it affects the acceleration and deceleration of flow across the surface. That is why we can think in direction of erosion and deposition. So, acceleration means it is convex, it is negative in that sense, and it will have erosion, and deceleration means it is concave, it will have deposition or may have less erosion or no erosion. Now, negative value A here indicates the surface upward convex. So, now it is a different scenario here. So, this is upward convex at that cell, and flow will decelerate it, because it is like that, that it is upward convex. Whereas, here the positive indicates the surface is upward concave here, and that concave will have deceleration. And of course, the value when 0, the surface is linear, and this example is C, where this is a straight line as shown here. So, this is negative, this is positive, this is 0. Negative means it will upward and it will decelerate here the flow conditions, whereas it will accelerate the flow condition, this is plus. Now, we can also have a general, total or standard curvature. These terms are also used in literature or by various softwares while deciding these curvatures. So, instead of plan or profile, we can have a total or standard curvature. So, general curvature is also total. 3 terms are used. Is the curvature of the surface itself not the curvature of a line formed by intersection of the surface with a plane? Like here, again that vertical plane you are having, and then when it cuts the surface, then this is the line which we are talking here. So, the general curvature or the total curvature or standard curvature can be either positive in case of convex, as you can see here, positive in case of and indicating peaks, as you have seen here, or negative or concave indicating valleys like here, middle part. And of course, indicating whenever you are having value 0, that is indicating no saddle or no flat surface, or rather flat surface. I say flat surface without any, or a saddle might be a situation, slight changes, or flat also. So, when you are having this general curvature is in concave, convex, that is positive, indicating peaks, and that means implying this or doing this analysis, implying digital elevation models, we can also identify which are the peaks and which are the valleys. That is what is part of our terrain analysis. Now, standard curvature basically combines both the profile and plan form or plan curvatures. And profile curvatures affect the acceleration and deceleration flow, therefore influences erosion and deposition, and plan curvature whereas influences the convergence and divergence of flow. So, if we combine both and create a standard curvature, we can we can together we can this will allow us to understand more accurately the flow across a surface. That will allow us to even predict what is going to happen in certain conditions. So, the diagram which we are going to have here, where in the columns here vertically, in the columns the plan forms are there, plan form curves are there, and in rows we are having the profile. So, in plan form column are positive, negative and 0. So, the first one is the positive, this is negative and this is 0. So, profile curvatures curves are also negative, positive and 0 going from top to bottom, positive, negative and 0 in all three cases. So, here things are convex, but still in certain conditions when it is upward convex, then you are having positive, but if it is divergent kind of situation, you are having negative. Similarly, here this is convergent and concave upward, you are having a convergent, again still convergent, still convergent. Here no changes because it is flat in that sense. So, no curved part is there for that flat, and that is the least possible scenario in natural conditions. Now, we can employ these curvatures, either total, plan or profile curvatures, for landform classification, which is based on a combination of horizontal curvature and vertical curvature. So, convergent will accelerate, divergent also accelerate, example here this one, and in this one this is convergent deaccelerating because now it is concave, and here divergent deaccelerating, and though it is it is diverting, but still it is deaccelerating. So, top two in the first row both are accelerating examples, and in the bottom two are deaccelerating examples, and also in the rows you are having convergent in first row and in second row in divergent. That means in natural conditions you can have various types of combinations, and accordingly things will vary on. So, a similar kind of thing, that classification of landforms on the basis of plan and profile curvature. So, here in this matrix you are having plan curvatures, here you are having profile curvatures, you are having convex, profile, straight and concave. So, these will influence each other depending on the conditions. So, the first one we call as nose type, just like a human nose. The second type of landform we say side slope, which is this one 2. The third one is the head slope, which is this one, and fourth one is like shoulder. So, you are having a kind of shoulder, and fifth one is negative contact. This is one negative contact, which is concave in terms of profile curvature is concave, and in plan curvature it is plan or straight, that is negative. So, these basically here arrows are indicating possible combinations of classifications, some we have already indicated. and that how these can be classified. The classification of total curvature or standard curvature will allow you to understand the terrain and from geomorphic or landforms point of view much easier. Now let us take examples at the value level, that is the cell value level. So this is our digital elevation model. This is the profile curvature output. Using that same digital elevation model, this is the plan curvature, and you can see that things are varying, and MB basically stands for no data here, or value MB is no data. So wherever in input if you are having no data, in output also whether it is a plan curvature or profile curvature you will have no data, otherwise you would have data. So of course this is also a neighborhood analysis. So based on that, if I consider say this cell which is 70, here in the profile curvature the value is minus 0.01 and whereas it is 0. If I consider 160, this is minus 0.07 and whereas this is positive value 0.06. So obviously the profile and plan curvature for the same area is going to be different, though the DM may be the same input. Now different methods again like Javergan and Thorne method for polynomial curvature values for a curve profile curvature which is giving value 0.29, and that means negative value means suggests that water will accelerate as it flows over the central point. So this is for the central point, this one. And in plan curvature the value is minus 0.36, and that means it is also negative value and suggests that water will converge as it flow over the central point. And the total curvature is when you calculate it is 0.01, and that basically indicates that positive, this is positive value, suggests that the surface is convex at the center point, which you can also feel here because there are 160 value and less than 165 values are there. So this is a convex scenario. Now using different methods and these plan curvature, profile curvature and total curvature along with digital elevation model. So first one, the top left is our input digital elevation model. This is the plan curvature which you can see, the profile curvature on the top right, and the bottom right is the total curvature. Of course all three will depict altogether different things, but if you see carefully you would find that the total curvature is encompassing both plan curvature and profile curvature. For example, in plan curvature you do not see the drainage network very clearly in this one, whereas in profile curvature you see these drainage network appearing in the white line. But in the total curvature, instead of white lines, these are appearing as black lines, and the details which were present in the plant curvature are also incorporated in total curvature. So total curvature can be more useful, that means compared to using individual curvature profiles. However, it depends on the application. If somebody is really interested from deposition point of view, erosion point of view, landslide point of view, flooding point of view, accordingly then appropriate curvature calculation should be done. In a standard GIS software like in ArcGIS, you may not get these facilities to calculate profile curvature, plan curvature or using various methods. But there is an extension which is in GeneSet available on net free of cost, where you can calculate 7 types of curvatures. As you can see, curvature types: profile curvature, plan curvature, tangential curvature, longitudinal, cross sectional, total curvature. and journal curvature. And it is telling what are the requirements and other things. So, again the tools may not be there, but on this site they have developed a tool which is allowing all kinds of calculations very easily. Whatever the output any such option creates, we must understand what is that, because after all we are going to use for some solving some real life problem. So, the output must be understood must be understood fully and carefully. Another example here, that a DM 50% transparency over the hillside. This I also showed you through demonstration, that you can bring a shaded relief model and digital elevation model together, and that digital elevation model you can choose a color palette and keep 50% transparent. So, in the background you are having hillside, top of that you are having a digital elevation model which is having colors. So, again 50% transparency example over plan curvature, 20% transparency, and over hillside, that is also there, pronounced valleys and ridges. That means now for the same area, if I use for the plan curvature, I can find out which are the ridges and which are the valleys very clearly. Just using a simple digital elevation model and hillside, I may not be able to identify valleys and ridges as easily, as accurately as in this plan curvature map. For display purpose, we are using the same method, that in the background you are having this curvature, plan curvature, and on top of that you are having DM with 50% transparency and using color palette. So, finally we come to the applications part, where many of them, many applications we have already touched, but very quickly I will go through, that the curvature map displays the shape or the curvature of the slope, which is very important at a local scale, because that is what it will control your divergent, convergent flows and ultimately erosion and deposition. So, a part of surface can be concave or convex. The output of the curvature functions can be used to describe the physical characteristics of a drainage basin in an effort to understand erosion and runoff processes. And these curvature values can be used to find soil erosion patterns as well as distribution of water on land, or even in case of landslide studies. Whereas profile curvature affects the acceleration and deceleration of flow, that is mainly water flow, and therefore the influences erosion and deposition. So, plan form curvature influences convergence and divergence flows. Further, useful to understand the physical characteristics when we drive these curvatures, total curvature or standard curvature, will allow us to understand physical characteristics of a drainage basin, also erosion and runoff processes. And it also will help us to determine the local factors of dynamics of overland and intra-soil water. Curvatures, as you know, influences soil moisture, because erosion and deposition, divergent and convergent flow will control the soil moisture conditions, may influence even pH values of soil, thickness of the soil horizons, because if erosion is taking place there will be less thick soil horizon, and if deposition is taking place there might be a more soil horizon depending the conditions, organic matter, plant cover distribution, etc. And curvatures are indicators of geologic lineaments, ring structures, and can be used to determine fault morphology as well. And curvature can be used to map accumulation, transit and dissipation zones of land surface, not only from that point of view, from snow or glacier point of view as well. So, with this we end this discussion about one of the very important derivatives after slope and aspect is the about the surface area, plane area and different types of curvatures. Thank you very much.